All right. Hello, everyone. Thanks for joining me today. I hope you are enjoying the conference so far. My name is Hossam Barakat, and I work as a lead consultant with Redify in Sydney, Australia. And today I'm going to talk to you about Istio Service Mesh and microservices. So my agenda for today is to talk about what is Service Mesh and why we should care about it. After that, we'll go through the Istio building blocks and its architecture. And then we will spend the rest of the talk showing you how would we apply the main features or leverage the main features from Istio, such as traffic routing, reliability, and observability, and applying them on a real-world microservices application. So why we should care about Istio? A lot of development teams have started their journey in breaking their monolith applications into a set of microservices, or building their new applications using microservice architecture. Microservice architecture in general has a lot of benefits, such as autonomy, modularity, flexibility, and all those kind of things. So in a microservice environment, each microservice should be deployed independently. And thanks to the container technology, I can easily achieve that. So I can containerize my application, put it on top of a Docker engine, and I'm done with having each service deployed independently. But the container technology itself brings more challenges, such as how could I have fault tolerance? So if one of the containers died, another one will be automatically spinned up to replace that faulty container. Or how could I have a scaling of the number of containers that I have to address the demand coming to my application? How could I have service discovery or load balancing for the services running on for my application? And thanks to the container orchestration platforms such as Kubernetes, a lot of those challenges have already been addressed. But there are a few more challenges that is still to be addressed, because those services will need to communicate with each other at a certain point. And previously, those services were living on the same host or even in the same process. But right now, we have split those services to be living on a totally different hosts. And this means that the communication between those two services is going to happen across the network. And with those communication happening across the network, there are challenges such as how could we have reliable connection between those two services? Or how could we have a secure connection so we can kind of encrypt the traffic between the service-to-service communication? Also, how could I have traffic routing capabilities to enable me to apply advanced traffic routing patterns such as canary-based deployment, so I can send the traffic or percentage of the traffic to the new version of the service, and as the service have more trust in it, I can incrementally increase the traffic going to it, and so on and so forth. But how hard could it be to have such reliable and secure connectivity patterns and traffic routing capabilities on network-to-network communication? If we take into consideration the fallacies of distributed computing, which are a bunch of false assumptions that as a developers, most of the time we make about the distributed systems. And those fallacies are the network is always reliable, latency is zero, bandwidth is infinite, network is always secure, topology doesn't change, there is one administrator, transport cost is zero, and the network is homogeneous. All of those assumptions are false assumptions. And it makes it really challenging to address the reliability and the connectivity issues with the service-to-service communication. And as developers, our first attempt to address those challenges is to start by building some libraries. So we can go with, if we are in a .NET world, we will have something like Bully to provide us with circuit breakers or retry patterns or having service discovery and so on and so forth with different libraries. So we end up with a bunch of libraries that we depend on to help us address those infrastructure concerns, because it's really undifferentiated heavy lifting. But at a certain point with a microservice environment, someone will come to you and will tell you that, all right, it makes more sense to write this new service in Elixir because of the actor model, or it fits this problem domain perfectly, or for any other reason. And it might be Elixir or Go or Haskell or whatever language that you would like to write your service in. At that point, you would realize that you have to solve the same problems that you have solved in your existing language in that new language. And again, there might be other libraries available to help you address those challenges, but by nature, the implementation between different languages might be inconsistent, because not everything will have a standard that you will need or you can follow. And the solution to that is to start applying another level of abstraction. And that level is extracting those infrastructure concerns from inside the application to be living outside the application. So if you have a service, that service will be split into two components. The first component contains your business domain and the application logic that you are trying to solve. And the second one is what's called a sidecar proxy. And the responsibility of the sidecar proxy is to include those infrastructure concerns, and it should be application language agnostic. So the sidecar proxy doesn't have to be aware that your application is written in C# or Java or Node or Go or whatever. It doesn't care. And this is the key concept that all of the service mesh platforms have been built based on it. And the service mesh is basically a dedicated piece of infrastructure that is responsible for connecting and controlling the service-to-service communication. And it's typically implemented as an array of sidecar proxies living alongside the application code. And that sidecar proxy is application language agnostic. And this is what's called the data plane. The second key component of a service mesh is what's called the control plane. The responsibility of the control plane is to accept the traffic rules from the users or the general rules from the user and send them to all of the services living inside the mesh, and mainly the sidecar proxies living inside the mesh. There are multiple service mesh platforms available in the market, but the one that I will focus on today is going to be Istio. So Istio is an open source service mesh that provides a uniform way to connect, control, secure, and observe services. So let's assume there are two services. Service A would like to communicate with service B. This communication could be across different protocols. So it could be HTTP 1.1 to gRPC or TCP or anything like that. Generally, without service mesh, the communication will be direct between the two services. But once we deploy the services to the service mesh, each service will have a proxy living alongside of it. And that proxy will automatically intercept the calls going in and out of my service. So if service A would like to communicate to service B, the call will go from service A to service A proxy, which then will go to service B proxy, and after that it will go to service B. And the response will go along the same path. And those are the data plane components of my service mesh. And in Istio architecture, there are also the control plane components. And the control plane components in Istio have three main components that you need to be aware of. The first one is the pilot. And the responsibility of the pilot is to accept the traffic routing rules from the user and push them to all of the proxies living alongside your application in the mesh. Second component is the mixer. And the responsibility of the mixer is policy checks and telemetry. So any service-to-service communication will happen inside the mesh, will have two calls, one pre-call and one post-call. So if service A would like to communicate to service B, the sidecar proxy will go and ask the mixer, am I allowed to go and proceed with that call or not? And if the mixer says yes, then the call continues. And after the call completes, asynchronously, the sidecar proxy will be sending some telemetry information to the mixer. And the mixer will be shaping those telemetry information and sending them through adapter pattern to external systems like Elasticsearch or Application Insights, as we will see later in more detail. And this enables me to have some observability features around my services, how my services are behaving inside the mesh. Final component from the control plane is a citadel. And citadel responsibility is a security aspect of the service mesh. So if we would like to have like an encrypted traffic between the services living in my mesh, the citadel will be generating the certificates and will be pushing them to the sidecar proxies, so we can have like something like mutual TLS authentication between the services living in the mesh. And this is the architecture components of Istio. So we have the data plane, sidecar proxies living alongside the application code, and it's application language agnostic. And the other thing is the control plane components, which is mixer, citadel, and pilot. All right. I would like to show you the features of Istio on Kubernetes. Istio itself could be deployed on multiple platforms like Kubernetes, Cloud Foundry, even virtual machines. But today I'll show you how would we use Istio Service Mesh on top of Kubernetes. By the way, how many of you have used Kubernetes? Nice, that's half of the room. That's cool. I just want to make sure that all of us have a shared understanding about two key concepts in Kubernetes. The first one is the pod. And pod is the atomic unit of scheduling in Kubernetes. Whenever you have a container that you would like to deploy on top of Kubernetes, your container is always going to be living inside a pod. the pod itself might have multiple containers living inside of it. And those containers will share the same network namespace, which makes the communication between those two containers seamless. And as you might have guessed, this is how would we have the sidecar proxies deployed on Kubernetes. So we will deploy our application as a container inside the pod, and the Istio proxy will be another container inside the same pod. The next concept that you need to be aware of when you are working with Istio Service Mesh on top of Kubernetes is the services. So service allows us to logically group a set of backend pods and expose them using a DNS name to be consumed by the clients of that pod. So in our example, we have two pods, pod B and pod C, and those two pods are exposed through a service, and that service has a DNS record. So my pod A could use that DNS record to communicate with those two pods. In addition to that, the service itself have a basic or a limited load balancing capabilities. So if a request were to go from pod A to the service will be load balancing those requests to the backend pods. All right, I'll spend the rest of the talk showing you the capabilities of Istio using a sample microservices application that I have built, which is basically showing a bunch of products. And when you click on one of the products, it will show us the product description as well as the reviews. And I have two versions of the reviews. The reviews V1, which is the one that we have right now, and reviews V2, and the difference between V1 and V2 are those little stars. So if we see the stars, this is the V2 of the reviews. The application itself consists of 3 microservices. The first one is the web, and this is the one exposing the front end to the users. And then I have a product catalog, which includes all the product information exposed as a set of RESTful APIs consumed by the web. And then I have the reviews, which is another microservice, includes all of the reviews information for all of the products exposed as a RESTful APIs. All of the data is in memory. There is no database here, just to make the example really focused on the service mesh capabilities. So I'll show you how would we deploy those services on top of Kubernetes, and then how would we have a proxy living alongside each service so we can intercept the traffic going between the services using the proxy. After that, we'll see how would we have traffic routing capabilities so we can apply canary-based deployment. So we send 80% of the traffic to V1 and 20% of the traffic to V2. After that, I'll show you how would we apply role-based traffic routing. So if the logged-in user is an administrator, I will send the traffic to V2. Otherwise, we'll send the traffic to V1. After that, we'll see how could we leverage the reliability features of Istio to make sure that our system is resilient, and we have testing of what will happen if the review service were to go down, or how could I make sure that for any network reliability issues, I can immediately issue a retry. We will see all of those things. Finally, we will see how could we have observability so we can have a holistic view of how my services are behaving on top of the mesh. So if something were to go wrong with one of the requests, how can I go and find out what happened to that request and which service was contributing to the failure of my request? So let's start by deploying our 3 services on top of Kubernetes. All of the source code is available on GitHub. I will share the link at the end of the talk. So the application is built with ASP.NET Core, and it doesn't really matter because as long as we have it in a container, we don't care with Istio Service Mesh what was the code built with. So in order to deploy the services, for each service, I'll be deploying the pods as well as a service living in front of the pod. And the way I will deploy the pod will be using a Kubernetes deployment object. To deploy anything to Kubernetes, there are 4 key parameters that we have to define. And the first parameter is the kind of the object that we are using. And in this case is deployment. Deployment enables me to have multiple replicas, like multiple containers for the same service. And it also has other features like rollout and rollback and other advanced capabilities that we will not get into today. Then we define the API version that we are communicating with, and the metadata, and in this case, we only have the name of the deployment. And the spec section, this is the key section that we will focus on. So first, we define the number of replicas, so we will have how many pods. In this case, we'll have 1. Then we have the template section. I'll get to the selector in a second. And the template section defines if we were to create a pod out of the deployment, how would that pod look like? So my pod will have 2 labels, and labels are a set of key values that could be assigned to any Kubernetes object. So we have two labels here, the app label and the version. And the spec section here is the spec of the pod. So we have multiple containers, but in this case, we have only one container, and this is the image of that container. So we have the image policy, if not present, this to allow the Kubernetes not to go and try to download the image from the internet. This just saved me a few seconds from the demos. And then the name of the container will be listening on port 80. And then we have a couple of environment variables. And those environment variables are the URLs of the product catalog and the reviews. And the thing to notice here is the DNS name that I'm using for the product catalog and the reviews for. And this is basically the name of the service that I will be that will be living in front of both the product catalog and reviews, and we will create them in a second. So this is how would we deploy our pods. The last thing that I wanted to touch on with the deployment is the selector pattern, and the selector is how would we glue the deployment object with the pods created for that deployment. So any pod will have the labels app and the Espresso Shop web. Those are the pods that will be attached to that deployment. So Kubernetes will keep track how many pods I have with those labels. And if the number of the pods didn't match what's expected, it will automatically try to resolve that. The next thing is the service object that will be living in front of my Espresso Shop web. And the service object enables me to have, as we said, a DNS as well as a load balancing capabilities. And we define a service by defining a selector, and the selector is a label-based selector. So we say any pod that will have a label with the key app and the value Espresso Shop web, any request will come to our service will always be going to those pods. And the type of the service in this case is the load balancer, and the load balancer enables me to accept the traffic from outside the cluster. And then the service will be listening on port 8090 and will be forwarding all the traffic to port 80. There is no specific reason for using 8090. It's just an arbitrary number that I picked up. So this is how would we deploy the pods as well as the service. And similarly, I have done the same thing for the product catalog. So we have a deployment for the product catalog. The differences are just the name and the images that I'm using. And then I have a service living in front of the product catalog. And as you can see here, the name here that I have defined for the product catalog is the same DNS name that I have used while I was defining the environment variable for the Espresso Shop web. And the next thing that I have is the reviews. And for the reviews, I have two deployments, one for the V1 of the reviews and another one for the V2 of the reviews. And in front of the reviews, I have a service. And that service will be forwarding the traffic to any pod with the Espresso Shop reviews. This means that the traffic will keep load balancing between the different versions of the reviews. And I can specify which version the traffic will go to by adding the label to the label selector, the version of the app. But I would like to leverage Istio to apply those traffic routing capabilities. So let's go and deploy the application in the first place. So I'll use kubectl, and I can provide the file that includes all my YAML objects. And this will go and immediately create the pods as well as the services. Switching to the Kubernetes dashboard, I can see that my pods have already been created. And if I open any of the pods, I can see that inside the pod, there is only one container. And going to the services, sorry. It looks like the tunnel is not working. So I'm using for the demos Minikube to run all the demos on my local machine. And in order to be able to access the load balancer services while you have Minikube, you need to use Minikube tunnel. And this will mean that all of the services will get IPs that I can use while I'm working on my local machine. So opening the Espresso Shop web will show us the application, and then opening any of the products will show us the product description as well as the reviews. And to see that the requests will keep load balancing between the different versions of the reviews, I have a little shell script that will keep querying the reviews and will show us which version of the reviews we are getting as in the response. So if I run this script, it will as you can see, it will keep hitting the reviews, and it will show us which version is coming back. And as you can see, the requests will be kind of balanced. It's not equally balanced because it's a small number of requests, but the more requests we have, the more the load balancing will be more visible in the responses. All right, the next thing that I'd like to show you after we deploy the services to Kubernetes is how could we start having more advanced traffic routing capabilities. And in Istio, there are two key components that provides us or enable us to have a traffic routing capabilities. The first one is the Invoice Proxy. And Invoice Proxy is an open source service proxy that have been built from scratch to support the cloud native applications. So it's built with C++, so it have a good performance, and it's also have a low memory footprint. It supports multiple protocols like HTTP 1, 1.1, 2, gRPC, and TCP. It also enables it changing, or it has a set of APIs that enables changing the configurations or the routing configurations through those APIs. And it's also have HTTP level 7 routing capability, so it can inspect like the headers of the requests, and this will enable us to say if a request have that particular header, do this or do that. The second thing is the pilot, and the pilot accepts the traffic routing rules from the user, push them to all of the sidecar proxies living inside the mesh. The pilot itself maintains like a canonical model of the services living on the mesh, and it also applies the adapter pattern. And this means that the pilot itself could be deployed on multiple platforms, such as Kubernetes, Mesos, or even virtual machine. And those are the key enablers of the traffic routing capabilities. But how can I actually define the traffic routing rules? The way Istio have enabled us to define the traffic routing rules by extending Kubernetes using custom resource definitions. So similar to the objects that we have used to create, or the YAML objects that we use to create a service or deployment, it's just a set of other objects that we can create. And there are few objects that we need to be aware of when we talk about the traffic routing capabilities in Istio. The first one is the gateway, and the responsibility of the gateway is to, if we would like to control the traffic coming from outside the cluster to inside the cluster, we need to have a gateway object. And if I would like to control the traffic going outside the cluster, then I need to have a service entry object. And to control the traffic for the service-to-service communication within the mesh, we need to have a destination rule, and the destination rules enable us to partition a service into a subsets, and we partition the service using a label selector, similar to the one that we used with the deployment as well as a service object. Then we use the destination rule to pack a virtual service object, and the virtual service object is the one where we actually define the traffic routing rules. And finally, we have a sidecar object. And the sidecar object enables us to tune the performance of the service mesh. So let's say we have in Kubernetes, we have 2 namespaces, and my services will never communicate with living in namespace E, will never communicate with any service in namespace B. So I can say, don't ever care or send any traffic or apply any traffic going to namespace B, and this means that the overall performance of the mesh will be improved because it's less processing will be done by the sidecar proxies. And obviously, the lower memory footprint as well. So if I would like to say any traffic going from the web to the reviews should always go to V1. The first thing that I will do is, because it's a service-to-service communication within the mesh, I will create a destination rule, and that destination rule will say, I have any traffic going to the reviews. This is a service that will have 2 subsets, V1 and V2, and we'll use the label selector to define those 2 subsets. And then we use a destination rule to create a virtual service, and that virtual service will say any traffic going to the reviews should go to V1 or go to V2 or split the traffic or anything like that. The destination rule as an object itself enables us to apply other capabilities such as circuit breaker or TLS settings. So let's see how would we start. Right now we have the traffic going to both V1 and V2. Let's see how could we have a sidecar proxy for each pod. And also, how could we create the destination rule virtual services so we can send the traffic to a particular version as opposed to having the load balancing that we have right now. In order to deploy the Istio service mesh proxies alongside the pods, there are 2 ways. The first one is we configure a particular namespace to say, for any pod that will be created in that namespace, automatically inject the sidecar proxy for each pod. The other way is to manually do this, and in order to do that manually, we can use istioctl, and this istioctl command have kube inject, and kube inject will accept the same YAML file that we just used to create the Kubernetes objects, the deployments, and the services. And what happens is the outcome of that command is, I need to provide the file parameter, is another YAML file, and that YAML file will be augmented with all of the parameters required to inject the sidecar proxy to my deployments. So you can see here the service object didn't change because it's not a pod, it's just a service. But the deployment of the reviews pods, as an example, will have heaps of parameters have been added. But the key thing is to notice here is the container section. So previously with the reviews, we had one container, but right now we'll have two containers. The first one is the one that we defined, and the second container is going to be the Istio proxy. And this is how Istio is actually behind the scene injecting those containers to my pods. So if I go and, let me just clear that, and pipe the outcome of that command to kubectl, it will go and create the pods with both the application container and the Istio proxy. And switching to the Kubernetes dashboard, I'd like to show you those pods. They are still creating, and they are running. So opening any of the newly created pods, we can see now that we have two containers, the application container as well as the Istio proxy. And if I get back to the application, it should be still the traffic keep balancing between the two versions of the services. So I'll keep getting V1 and V2. But now, since we have the Istio proxy in place, I can start creating the destination rules and virtual services that will enable me to define which service the traffic should go to. So let's start with the destination rules. And it's very easy to define a destination rule. So destination rule is basically you define the host, and the host is the service, the Kubernetes service that we created. So we say for the host Espresso Shop Web SVC, we have only one subset in this case, and it's V1. And the way we define the subset is using a label selector, and we are using the version label to define the subset V1. And similarly with the product catalog. And finally, for the reviews, we have two subsets, V1 and V2. And we define that again using the label selector, which is the version label. So this is how we define the destination rule. Once we have the destination rules in place, we start creating the virtual services. So for the virtual services, I have a virtual service for each microservice. And again, using the name of the, or the DNS name of the Kubernetes service, we say for that host Espresso Shop Web SVC, for any HTTP traffic, route that traffic to the destination, and in this case, it's the same host, and which subset that we are using. And this is why it's important to have the destination rules in place with the subsets created so we can use them to define the traffic routing rules using the virtual service. I have the same another virtual service for the product catalog, and finally for the reviews. And this is the most important one, because in the reviews we have two versions, V1 and V2. But once I deploy the virtual service to Kubernetes, it will be always routing the traffic to V1 or always routing the traffic to V2. So if I want to go with V2, I'll just change this to V2. So let's go and deploy the destination rules as well as the virtual services. As you can see from the YAML file, they are just the same way we defined the previous Kubernetes objects. So let's go with, since they are just yet another Kubernetes object, we can just use kubectl to deploy those objects. So I'll deploy the destination rules first, and then we'll deploy the virtual services. So right now, if I go to my application, I should always get V2. And as you can see, as I keep refreshing, it will always showing me the V2, which is the one with the stars. And if I would like to send the traffic to V1, all I have to do is just change the virtual service to say any traffic going to the reviews should always go to V1. And I deploy this virtual services again. refreshing, and now we have V1. So this is how easy it is to start controlling the traffic between the services using the service mesh. And the good thing with that is I don't have to change my application code or deployment configurations or anything. It's just from operation perspective. I just change the Kubernetes object, and it will go and immediately start applying those traffic routing rules. And since they are YAML files, you can have them in your source control, and you have versioning and everything as you do with your normal source code. The next thing that I would like to show you is how could we start using that virtual service to apply a canary-based deployment. So we would like, instead of sending all the traffic to V1 or all the traffic to V2, I would like to send 80% of the traffic to V1 and 20% of the traffic to V2. And the way you do this is by updating the virtual service that we have just created to include two destinations. So we say for the HTTP traffic, route the traffic into two destinations, the V1, which is Espresso Shop reviews, and we define the subset. And the additional parameter that we have here is the weight parameter. And here 80 means 80%. And the other destination is V2, and this means it's 20% of the traffic. So once I deploy this, if I refresh the browser, I will see most of the requests going to V1, and then some requests will go to V2. It's hard from the browser to see this, so what I'm going to do is just, I will open like one of the pods, and I will run a shell script that will go and hit the reviews. So we can see more stuff. So we can see most of the requests are going to V1, and then some requests goes to V2. Apparently it's all V1 now, but again, because the traffic routing, it's a bit hard to see the exact pattern with a very small number of requests, but as the number of requests increase, you can see the exact percentages. And you can use this to apply, like if I rolling out a new version of my review service, I can say, all right, I'll send only 1% of the traffic to that service. I have more confidence in the service. I start increasing the percentage till all of the traffic goes to V2, and only small percentage of the traffic goes to V1. And all I have to do in order to do this is just changing those numbers from 20 to 100, and this to be 0. And those are just enablers. It doesn't have to be exactly using those YAML files. You can have those incremental rollout more automated in a more automated way, so you don't have to fiddle around with the YAML file all the time. The next thing that I would like to show you is the user role-based routing. So I have a little login feature in my application, and I'd like to apply if the logged-in user is an administrator, or the role of the logged-in user is an administrator, then send the traffic to V2. Otherwise, send the traffic to V1. And this enables you to apply, if I'd like to roll a new version and would like to test this version with internal users or something like that, I can easily apply it with Istio. And Istio enables us to do this because for the service-to-service communication that I have in my application, I have the user role as a header in all of the requests between the services. And since Istio have a level 7 capability, I can go and inspect the header and say, if the request has a header with that value, then do this or do that. So, and to do this with the virtual service, I can say, for the HTTP traffic, if the request has a header, and that header has the key with the key user role, and the value of that header has or contains the word administrator, then route that traffic to V2 using the destination object. Otherwise, route the traffic to V1. And this is how easy it to apply the user-based routing. The virtual service itself might have multiple rules applied within the same virtual service, and there could be precedence. So we can say, I would like to have 80/20, and at the same time, I would like to have a HTTP level 7 capabilities or routing capabilities and stuff like that. So let's go and deploy that. So I will log into my application using admin. And no, don't do that. Once I log in here, since the logged in user has the role administrator, we will always see the reviews v2, which is the one with the stars, regardless how many times we refresh the page. But if I copy the same URL and open another browser without a logged in version, I can see that I have v1. Also, if I logged into the application and used a non-administrator user, it will show me the v1. And this is how easy it is to apply those traffic routing capabilities to see and start controlling the rollout of the new version. The next thing that I would like to talk about is the reliability. And in a microservice environment, there might be more than one microservice collaborating with each other to return a response to the customer. And in a microservice, I would like to have a more resilient system. So if something were to go wrong with one of the services, I don't want my whole system to go down or there is anything like that. And the way we do this is we would like to have something like a retry pattern. So if something were to go wrong with the network, I can easily retry that request, or I could have fault injection. So I would like to test that if the review service were to go down, as an example, my whole application doesn't go down. And previously I had, like, without my Istio service mesh, I had to fiddle around with the configurations or the network firewalls to disable the communication to a particular service so I can verify such behavior. But with Istio, I can easily apply that by using a fault injection features from Istio. Finally, there's a circuit breaker, and circuit breakers enables me, if a service doesn't have enough capacity to process the requests that it's accepting right now, then we can give it a slack to breathe and process whatever requests it has, and then start sending more requests back to that service. So what I will show you is the timeout pattern. So in my application, I have applied a little delay. So some products, if we open them, it will take like 6 seconds. But with the timeout, I can say, regardless how long does it take to actually process that request from a particular service, always time out in 500 milliseconds. And this means that if one of the services is really, really slow, my end users are not impacted by that, and they don't have to wait for a very long time. So the way you do this is by using the virtual service. It's really simple, and say, for any HTTP traffic, route that traffic to v1, and always time out in half a second. And this means regardless how long does it take the review service to come back to me, it will always return within 500 milliseconds. So I'll show you, before I deploy that for some of the products, if we open that product, we will see that it takes like 6 seconds to come back, as shown here. So it takes like 6 seconds to return a response. And we can see that the response here is no reviews yet. And once I apply the timeout, I will see that it takes like slightly more than 500 milliseconds. So let's deploy the timeout. And now getting back to the browser, I will refresh the page again. And as you can see, it took like 515 milliseconds. But the review section right now is showing failed to retrieve the product reviews. And this might not be the same way that you will approach it in your production environment. You might opt in for just removing the whole reviews widget altogether. But this is also enables us to make sure that the system will not have a very slow response to the customers. The other thing that I would like to show you is the fault injection feature from Istio. So what if the review service were to go down? How would I verify that the application will not crash or will show like an exception page or error page or to the customer or anything like that? And the way we do this is by using the fault injection features from Istio. So if we go to fault, we can go and say, all right, I will update my virtual service, and I would like to inject a fault of the type apport. And I would like to apply this fault to 100% of the traffic. I can choose the percentage of the traffic. And then the status code that will be coming with that fault response will be 500. And this will enable me to test if the review service is down, how my application will behave. So let's go and apply that fault. And now it was taking 500 milliseconds, but once we refresh now, it took only 16 milliseconds because the request actually didn't go to the reviews and there is nothing has been processed. The Istio service mesh immediately sent the response to the web. And again, since I have applied the logic to handle that error, my application didn't crash. But before I applied that logic, my application was showing an error page that the whole page went down because it couldn't reach to the review service. The last pattern about is a circuit breaker. And circuit breaker means some of the services might not be able to handle more requests at a certain point. And if that's the case happened, what I can do with Istio is I would say for a particular number of errors, so let's say if I have 5 consecutive errors within 10 seconds, then eject 80% of that service. So the traffic will not go to that service. And I will eject it for 3 minutes. After 3 minutes, I will start sending more traffic to that service. And if the service is healthy, we'll keep sending the traffic. If the service is still unhealthy, so we have more errors within 10 seconds, we will eject again 80% for 3 minutes, and so on and so forth. And this is how easy you could apply a circuit breaker. It doesn't mean that you will not have a circuit breaker logic in your application, because the difference is with the circuit breaker that you have in Istio, doesn't have any fallback logic in place. So if the service review service is down, for some application, you might want to opt for a stale data that you have or a cache data or something like that. But this doesn't, with Istio, you will not get the same benefits. But again, it's one tool that you can use in order to have a high-level circuit breaker features. The last thing that I would like to talk about is the observability features from Istio. In a microservice environment, generally, each service will be generating its own logs. And ideally, you would be sending those logs to a centralized location. And if something were to go wrong with one service, you would like to go to that centralized location. It could be Elasticsearch, Application Insights, or anything. And you would like to find any logs relevant to that request. And we usually do this by having a correlation ID. So you have a request. Each request will have a correlation ID, and you pass that correlation ID to all of the services. So each service writes its own logs, will include that correlation ID. And this provides us with what's called the distributed tracing capabilities. So if something were to go wrong, I can easily identify which service had the error and what was the context around that, and I can easily troubleshoot and diagnose what was going on. The next thing with observability is how are my microservices are behaving. How many errors did I have? How many success? What is the volume of the requests coming to my application? What is the latency? What is the average duration of the requests in my application? And are there any different behaviors for my microservices based on the clients or not? And even better, I could use all of those matrices to build alerting capabilities on top of them. So if something were to go wrong with any of the services, I can notify the right people so they can proactively log in and troubleshoot if something to be changed or something went wrong with my services. And the good thing with Istio, we can get all of those benefits using the mixer component. So as we said at the beginning, any request will happen between service to services asynchronously. The sidecar proxy will be sending telemetry information to the mixer, and the mixer will be sending those, will be using a platform adapter pattern to send those telemetry information to external systems, such as Elasticsearch or any other system. And this enables us to have those holistic view of my microservices. And the good thing is, Istio itself comes out of the box with a lot of adapters that we can use to plug them into Istio, and those adapters will be automatically working without it changing any of the application code. So you don't have to install any library to your application that will be sending the logic. It just happens out of the box from Istio without it changing any of the application code. And there are heaps of adapters such as AWS, Prometheus, Jager, Graphana, and heaps of others. And if you didn't find your system that you are using in those adapters, you can build your own adapter to extend Istio. I'll show you two demos. I will not show you how would you actually like configure an adapter to connect it to Istio, because it's really well documented in Istio documentation. But I would like to show you, after you configure those adapters, what are you going to get from a distributed tracing and matrices perspective. So the first demo is about Jager, and Jager is an open source distributed tracing platform that has been built by Uber and open source it so we can use it. And the second, which will help us to identify for those cases that we had a very slow response, which service is contributing to that delay. The second one is going to be about Graphana, and Graphana it will show us, it's again another open source platform that we can use to have matrices, so we can have dashboards and we can see how the services are behaving from success rate, failure rate, latency, and all those kind of things. So before I do that, I just want to make sure that we have healthy APIs. So I'm just resetting all of the services to send the traffic to V1. And then let's go and generate some traffic here. So the first thing that I will show it is Jager, and I'll go to the slow product that I have in my application. And what I have done is, for the correlation ID of any request, I send that correlation ID as a response header. So if something were to go wrong with any of the requests, I can go and grab that correlation ID, which is X request ID. And then I will go to Jager, and Jager itself automatically can see all of the services living inside my mesh. And I can go and, for example, I can select reviews and find all of the traces relevant to the reviews service. But the good thing also, I can go and search for a particular trace, and this will show me all of the logging information for that particular request. So with Jager, I can see that for that particular request, there was 2 calls, one from the Espresso Shop web to the product catalog, and that took 4 milliseconds. So all good. The other one is went from the Espresso Shop web to the reviews service, and this took 6 seconds. And this means the review service was the source of the delay in this particular case. And as you can see, there is also, it's very easy, so you can see the spans, and if you have multiple operations happening in place, so if the review service were to call another service, you will see all of the dependencies in there. And to have that kind of distributed tracing spans and all those kind of things, I had to do one small change to my application code, which is including a bunch of headers for all of my service-to-service communication, which are like those 6 or 7 headers. And it wasn't a big change because in my microservices environment, I already sent the request ID for the logs, so I just changed them or added them like those headers, so it can give me this nice visualization. If I didn't add them, I will still get all of the telemetry information, but it will not be like nicely visualized as a hierarchical view as we have seen with Jager. With Jager as well, I can see the dependencies between the services. So I can see something like that, which will show me that I have like 3 services. It's not the nicest graph, and there are better presentations or representations of dependencies, but it will show me that I have 3 services: the web, product catalog, and reviews, and all of them are the dependency that the web depends on the reviews as well as product catalog, and the 3 of them depends on the mixer. And this is also coming out of the book. So the more services you have, you can have a better understanding for the dependencies between those between the services you have in your environment. The last thing that I would like to show you is Graphana. And because our environment just will refresh a few pages, and Graphana will show us some matrices. So it will show us the success rate, the failure rate. So as you can see, it will show us how many requests coming to my services, and it's automatically discovering the services living in the mesh. So I can get the review service, and I can see how many requests coming to the reviews, and I can see it also by a client or by a consumer. I can see the success and failure. I can see the different versions of the reviews, as we can see here. So I can see V1 and V2. And the good thing, I can also use all those telemetry information and build alerting on top of that. And I didn't have to change any of the things in my application code to get those telemetry information or all those presentation or graphs and dashboards. So the key takeaways that I'd like to make sure that you guys get out of this talk are: Istio is a service mesh platform that provides us with traffic routing, observability, and security features. Istio consists of a data plane and a control plane. The data plane is a sidecar proxy living alongside the application code, and in Istio, it's the Invoice Proxy. The control plane consists of 3 components: Pilot, Pixar, and Citadel. The Pilot provides us with traffic management, service discovery, and Mixer provides us with access control, telemetry. Citadel provides us with the security aspects from traffic encryption, authentication, and authorization. We have seen a lot of the tools or demos about the traffic management, and we have seen the telemetry from the Mixer. We didn't get to see the access control and the encryption, but again, you define those configurations using YAML objects similar to what we have done, and there are heaps of documentation around it. From resources perspective, all of the demos that I have shown today are available on that GitHub link. If you would like to learn more about Istio, there is a very good platform called Katacoda. It's really awesome. You can just try to have a bunch of tutorials that you can try out Istio inside the browser, so you don't have to install anything in your local machine or on a cloud environment or anything like that. Finally, if you'd like to learn more about Istio, the Istio documentation is really well documented, and it doesn't have like a reference documentation only. They also have practical examples of how would you apply Istio features on a microservices application. The slides themselves are available on that bit.ly link, and it includes all of the resources and everything. And that would be it. Are there any questions? All right. So, all right, that's it. Thanks a lot for attending the talk. Thank you.